Okay, so for 9.4, this is our last section for this unit. And I know it feels like it's flying by, and it is. Welcome to the end of the year. It always feels like it's flying by. So last class, we applied the properties of permutations. Properties like factorial and using the P button on our calculator that is buried there. So today we're going to talk about combinations. They're very similar to permutations in kind of the way that we write them out. But we just use them in different cases. So at the top of your notes, I have this kind of idea here, okay? Suppose in school you need to form a group of 4 people to work on a class project, and in softball you need to form a batting lineup of 9 people. How would the possibilities of forming a group for the project be different than the possibilities of forming a lineup? So obviously 4 and 9. Don't think about it in terms of the numbers. So if you're working on a group project, and the 4 of you are going to be working together, do you care in which order you pick those people for your group?
No.
No. Whereas for a batting lineup, right, don't you want your strongest batter first or third or whatever the strategy is there? Order is going to make a big difference. Because when you look at your 9 players, you're going to say, well, I don't want that player going first, second, third, or fourth. So I don't even have that player as an option. So when order matters, you're going to use permutations. Right? So we just got done with permutations. It's all about when order matters. We're going to use combinations when orders don't matter. So hopefully you can read that. An arrangement of objects in which order does not matter. Order does not matter. And I did put the equation in there if you would like to copy that in. But we hopefully know how to find this on our calculators, so that we will use our calculators to calculate this for us. And you'll notice with permutations, I used a P, and with combinations, I'm going to use a C. So on your calculator, under the probability section, right below factorial and permutations, you've got combinations. So in today's class, we're going to do a lot more with working with a card deck, with a deck of cards, okay? You have that cheat sheet in the back of your notes of a deck of cards. I don't, right? No, but nobody in this room has to be a gambler, although has anybody in here played a little poker?
What do you define as a little?
So, right, say we're playing a 5-card stud or something like that, or 5 cards, whatever, something wild. How many different 5-card hands are there out there? Does anybody have like a guess as to how many 5-card hands are out there? Is it in the hundreds, tens of hundreds, thousands?
10,000s.
Like a million? So the thing is, do you care in which order you get dealt those 5 cards?
No.
No, right? They're eventually going to be part of your hand. You do not care in which order the dealer dealt them to you. So that's why we're going to use combinations to calculate this. How many cards are in a deck?
52.
And I want to choose, so you'll notice what I'm going to say instead of pick is I'm going to say choose 5. Let's go and put this in our calculator to figure out how many 5-card hands are there. So you're going to type in 52 and then math. Go to the probability category and make sure you choose the NCR1. Yes. This is why, right, people that are good at math and play poker have quite an advantage when it comes to this stuff, because I don't think you necessarily understand how much math can go into just one deck of cards. There's almost 2.6 million hands out there. Right? Like, that's crazy to think about. But every single card in a 52-card deck is different than the next one. right? There are a combination of diamonds and clubs and face cards and whatnot, but since every card is independent of the next one, this is why you get so many distinct different hands. So let's do some more examples. Suppose there are 22 people in your class. If you were to pick 4 to form a group, how many different ways could this be done? How would I just write this?
22 choose 4.
22 choose 4. That's all. So go ahead, pick up your calculator, type that in. Make sure we know how. We got 7,315 different ways to do it. So in your worksheet packet, you have another one of these worksheets, right? Those really kind of short questions. I want you to go ahead, work with a partner, work by yourself, whatever you'd like. There are only those 6 questions. I want to make sure we know how to kind of outline this and write down the different ways in terms of combinations with a C in the middle. So I'll give you about 4 or 5 minutes, and then we'll come back together. We'll go over the answers together.
What's the catch?
Just want to make sure, right? The last time we did this with permutations, it wasn't necessarily so easy. Now I feel like we're getting the hang of this a little bit more, so I'm glad you think it's easy. That's what I'm going for. We're going to get into some harder questions, right? None of these are about probability yet. It's just about finding a sample space. We haven't done probability yet. It's just. Okay.
The notes are 2 plus 2.
All right, last minute to finish up these, and then I'm going to read out the answers. Oh, yep.
Elmo toys. 10 wild shot. Alright, can you grab one of the last 6 Elmo toys? What if one of them dies?
Don't be so morbid, Carter.
So wait. Never know what someone's gonna be willing to So this one's like about different sets and combinations, right?
I read
this
on
is
one
about
quiz and I
order
almost
doesn't
forgot that
matter.
I said emo
A
guys.
different way, because if you so say for your person right now.
It took me a second. I thought it spelled something for a second.
Lower number, and then I never
Like the last one too, they repeated
Same.
like 10,000 things and it was
So,
still like there's
right,
some
like
reason.
that one we had Oreos, I think we're gonna get smaller, the order doesn't matter. So it's almost like they're taking out all the repetition and double counting for you in these formulas.
Okay.
All right, ready to go over them? Number 1 is 10 choose 6, which is 210. Number 2 is 10 choose 5, which is 252. Number 3 is 13 choose 5, which is 1,287. Number 4 is 9 choose 5, which is 126. Number 5 is 10 choose 6, which is 210 again. And number 6 is 11 choose 6, which is 462. Hopefully we feel at least confident, right? How to type this into our calculator, how to write out kind of what we're looking for. So let's come back to our notes and let's start to do some probability questions. Or just different ways to think about these. All right. So, anybody know what happens if you get 5 diamonds? What's that called?
It's a flush.
It's a flush. It's only a royal flush if you start with ace, king, queen, queen, jack. So, what is the probability that I get all diamonds?
Oh,
What's the probability that I get a flush, right? A flush
low.
exactly. So, I'm assuming that everybody knows like what beats what, right? 3 of a kind beats 2 of a kind. A full house beats a flush. There's all these different levels of what beats what. And how do you think they figure out what beats what?
Carefully.
Whatever is the hardest to get, whatever has the lowest chance of actually showing up, that's how they figure out what beats what. So let's talk about, when we asked about probability, right, we need a numerator and denominator. So we've already figured out what our denominator is, right? It's 52, choose 5. How many diamonds are in the deck?
13.
13, and I want to choose 5 of them. So that's your numerator, right? You're only narrowing it down to the 13 diamonds that are in the deck, and you want to choose 5 of them. So this ends up being quite a large number.
No kidding.
At least right on the bottom. It's 1,287 over our 2.6 million. Which ends up being only about a 0.05%, that is already in percentages, chance that you're going to get a flush. It's hard to get,
Oh yeah.
right? This is why, right, if you play a 5-card game, try to make something wild, so it makes it a little bit easier. But that's how we figure out these probabilities. All right, we're going to keep going with some probabilities, but we're going to amp it up a little bit. Because I'm assuming if we've done at least one example like this, we can kind of figure out a lot of similar examples like that. Let's not overcomplicate things for just one question, for just 1 second. So I go into a store and I say, okay, I'm going to either buy a candy bar or a soda. I only have $1.10 on me, so I'm going to either buy a candy bar or a soda. If there are 5 choices of candy bars and 7 choices of soda, how many different options do I have?
35.
Wait, there's how many?
No, just 12.
Just 12. Just 12. So a lot of times when you see the word or, you're going to just add those options together. Okay? All right, let's look at our next question. A coin is flipped 5 times. Find the probability that the result is a heads at least 4 of the times. Okay. So I'm flipping a coin. Let's talk about the denominator for a second. Okay? When I flip the coin the first time, how many options do I have?
2.
And then the second time?
2.
And then the third time?
2.
And the fourth time?
2.
And the fifth time?
2.
Now, in my numerator, I want heads, right, to show up either 4 times or 5 times. So I have an or in there. I either want 4 heads or 5 heads. So let's imagine that as I flip this coin, I'm just writing down like H and T, H and T, T and H, whatever I end up getting. So out of the 5 that I write down, I want 4 of them to be a heads, to be an H. Or I want all 5 of them to be an H. Challenging, I know. Challenge.
32.
Whether I decide to give up.
Don't give up, don't give up, don't give up. So I end up with 6 out of 32, 3 out of 16. Simplify down my function. And I figure, right, as long as we know how to type this stuff into the calculator, I would need to make sure, right, the calculator knows that that's the whole numerator. But we're just, right, we're doing some more challenging examples. We don't do these all the time, okay? Let's look at the next one. Oh, wait, did I miss? Well, I guess we can talk about this now. It's there, so let's talk about it. So several years ago, all of the Wendy's bags that were in circulation had this claim. We figured out that there are 256 ways to personalize a Wendy's hamburger. Luckily, someone was paying attention in math class. So we need to figure out if they're right or not. Okay? That's what we're going to try to figure out. Now, this was a few years ago. If you go to Wendy's now, they have like all these other toppings you can put on your hamburger, like chili, or maybe at some point they had it. But at the time, here were the 9 potential toppings that you could choose from. Now, like bacon and cheese are going to charge a little bit more for, but there's still options, right, of adding to your hamburger. We have pickles, lettuce, tomato, onion, ketchup, mustard, mayo. So, how many different ways are there to choose all these things, to personalize it your own way? I want you to think about it, and then I want you to talk to someone around you, a couple people around you, see what they're thinking. Notice, though, that we were just doing or-type questions, where I have to think about this situation or this situation, and when I usually have those ors, I'm going to be adding those options together.
I get 2 cheeses. Or do I?
Okay, let's just assume that if you say bacon, you can't be like, and then quadruple the bacon. No, just let's, right? At least I don't think that's what they were going for when they say their bags.
The more bacon.
All the bacon.
So,
This is one. That means you have one. So you show the 9 things, right? You don't have to get all 9. Or
I don't know if you
or
think
1 or nothing.
but I see 9. Alright, so I have where I'm going with. There's gotta be an easy way to write that out, right?
I'll give you the answer. I'll tell you what that is if you just write down what the equation is. Justin already got it.
I hated the look that you gave me as you.
That's it, because I was like, you got it.
I was like, I don't want to think.
I'm not going to make you type it in. Unless maybe if it's a like bonus question on the test.
Alright.
Yes. 9 shoes. You know what? I don't want anything on my burger. Nothing.
9 choose
Oh,
0.
10.
Wait, 10 choose 9?
What's the 10th thing? There's only 9 options.
You know, if you don't want anything on your burger,
So how many of these am I choosing?
0.
Yes. And then this guy over here, he said, you know what? Is one are you adding those? 9 choose. 0 plus 9 choose 1. Yes. Don't put it in your calculator. I'll tell you the answer. All right, let's come back together and talk about this because I think a couple of groups have already figured this out.
I just.
So you've got like my 9-year-old daughter that just hates anything on any of her food and they can't touch and all that kind of stuff. So she's going to be 9 choose 0. She's not going to pick anything on that list. But then you also have to consider my son, who just wants only ketchup. Please just only ketchup, nothing else. And then you got to consider all the other options, right? 9 choose 3, all the way up to 9 choose 8, plus, you know, the person that wants everything on their hamburger.
That sounds awesome. Super great.
So you add all these up, and no, I'm not going to make you type these all into your calculator right now.
Oh, dude.
Do you think we get 256?
Oh, heck no.
We get 512 different ways to so the thing is, right, you're saying that's it? When we were talking about permutations last time and we had factorials, numbers got big really, really fast.
Yeah.
With combinations, right, the idea is that you don't care if your cheese goes on top and then your lettuce and then your tomato and then your ketchup, and, right? Order doesn't necessarily matter.
God.
I mean, granted, right, that's why some people are sandwich artists, they know how to make it in the right order, but ultimately, if you go through the drive-thru and you get like lettuce, tomato, and onion, you don't care in which order they put it on. So the numbers actually don't get, maybe some of us, right, are not as perfectionists, but the real answer was 512. And it didn't take long for somebody to bring this to Wendy's attention. You have miscalculated the number of ways. And they said, well, too bad we have, 10 million bags printed, so.
It is what it
I guess
is.
what it is.
How many people had to look at that and like figure it out and prove it? There was that many people wrong.
It was a math class that did it, and they wrote letters to Wendy's, and yes. So it's right, like when you're sitting there in the drive-thru, you're probably not thinking about this, but there was one math teacher that was like,
even in like the production, like people at Wendy's had to like there had to be mathematicians there trying to figure it out.
I know.
Like how many people proved that before it actually got sent out?
Imagine being bored and you're
So
working
like
at
one of
Wendy's
their
and you're
things,
trying
one
to
of their
figure it
pushbacks was, we charge extra for cheese and bacon, so we won't consider that. But if you do that, it drops it below 256. So I don't know, just always something to think about. Ben, can you please get off your phone?
Yeah.
Okay. So I don't know. That was just a little brain break because I knew that we were going to be feeling a little bit overwhelmed with all these
I want to
probability
go back to
questions.
cards.
So let's come back. We're going to do a few more problems together.
I like 50.
Not this one.
Oh, hello.
A math department has a large database of true and false questions used to create exams. A new test is created by randomly selecting 6 questions from the database. What is the probability that the new test contains at most 2 questions with a correct answer of true if the questions in the database are equally likely to be true as they are to be false? Notice we always have to have this, like, and especially on like an ACT question, they have to tell you all of these things are equal or else you're gonna, right? Assuming like when you flip a coin, it really is 50-50, it's not an unbalanced coin, that type of thing. All right, so let's talk about our denominator. How many options for true-false questions?
6, 2.
2, but I have 6 of them. So it's going to be 2 to the 6th,
Oh.
right? True or false for this question?
64.
True or false for this question? True or false for this one? Now my numerator is going to be kind of like the couple previous questions and the Wendy's option. I have to think of some different situations. So at most 2 questions. So I could have 0 questions that are true, 1 question, or 2. So I have all these 6 different choices, and they either need to be, none of them need to be true, 1 of them needs to be true, or 2 of them. Those are the things that I'm looking for.
What is 6 choose
6 choose 0, there's really only one way to do that. I choose 0.
Okay.
Okay, I actually calculated out so you wouldn't have to do it. We have 22 over 64, which is 11 out of 32. Questions on those? I know, these may be the types of questions that when you leave the classroom today, you want to go back and reread over. I know that, especially with probability, students often say, well, I can wing it, right? So a little common sense. These types of questions, I recommend you review them. I do. These are the last 3 questions we're gonna do today. I do like to do like complement of events, but I don't want to overwhelm anybody today. If we have time next class as we're reviewing, we can talk about them a little bit, but I don't plan to put them on the test. So we're gonna go back to our deck of cards. Using a 5-card hand, okay, so we're gonna assume that we're gonna get a 5. We're gonna choose a 5-card hand, and notice we're not gonna find probability until we get to letter C. So A and B are just going to be our sample space, or just going to be our denominator. How many different ways can I do this? I want to get a king and any other card. Notice the word and. When we had or, what did we do?
Add.
When we have and,
Multiply.
yes. It's like a big deal in probability, knowing those 2 things. Yep.
So would it be 52 choose?
How many kings are there? Let's talk about each of these completely separately. 4. Choose how many? 4. Right? I want to pick all 4 kings out of the deck, but I don't care if I get king and then a 2 and then a king, king, king. Right? It doesn't matter in which order that they're coming out of the deck. So that's why I'm using combinations and not permutations. Now I have and, so I'm going to multiply. How many non-kings are in the deck?
48.
50.
48, choose 1. So here's the thing. How many ways are there to choose 4 kings?
4.
There's only one way to do it because order doesn't matter.
Yes.
So I'm going to take out those double counting of, oh, I got a club and then a heart. Well, what about a heart and a club? Doesn't matter when we're talking about decks of cards. It mattered last class when we were talking about permutations. So there's really only one way to get all 4 kings. That's why it's so hard to do. But there are 48 ways to get that extra card in the deck of cards. So when we talk about a 4 of a kind, right? A 4 of a kind doesn't really come up all that often in poker. You know why? What's the probability it'll happen? 48 out of 2.6 million decks of hands that we just talked, right? Like that is why it's so hard to get 4 of a kind. And harder than a flush. All right, now the next one has the word or. That tells me I'm going to add. So I've got to think about, right, it's a 5-card hand. Let's talk about first if I want to get just 1 spade. How many spades are in the deck?
13.
And I want 1 of them. But I've got to talk about all the other ways to get the other 4 cards. How many non-spades are there?
50.
No.
48. 47.
39.
Oh, no.
Because I've got to consider all the ways to get 4 other cards that are not spades.
Oh, I see.
So, right, I'm thinking about a 5-card hand here. It's all about, I've got to think about all the different ways I can get 5 cards in my hand and only 1 of them being a spade. But this was just the 1 portion right here. I now have to add, that's right. And I want to maybe get 2 spades. 13 choose 2
39 choose 4.
times 39 choose, I only need 3 more cards, right? 5-card hand. So this one, right, I mean, if you've ever played any kind of like, card game, what are the chances you get a spade in your hand?
It's actually high.
It's actually pretty high, right? Like, there's only four different suits, so it's probably a pretty good chance that I'm going to get a spade. This ends up being over 1.7 million different ways, right? Because it's really not that weird to get a hand that has a spade in it. Kevin?
So for letter A, when we have to do 4 choose 4 for the king, how come we can't think of it as I have 52 cards to get, I need 4 kings out of it?
So I'm not okay, so I'm only talking about a 5-card hand right now, right? So if I wanted to, my sample space of probability This is my numerator we're going to talk about here. My denominator would be 52, choose 5. Okay? All right, let's look at letters. Yeah, question?
For letter B, how come you? Oh wait, never mind.
Are you sure?
Yeah.
Okay. I know. You will, I'm trying to, let me double check on the homework, but I'm pretty sure there's a good amount of, you should see a good amount of similarities on your homework to the questions we're going over in class. All right, so our last one, probability of getting exactly 3 hearts. So here's where, Kevin, right? My denominator is going to be 52, choose 5. Now my numerator, I still have to get 5 cards in my hand. But I want exactly 3 of them to be hearts.
Should be 13 to choose 3.
Yep. But what about the other 2 cards? They can be anything as long as they're not hearts. Exactly. 39, choose 2. Okay. Let's wrap it up there. Let's have this be, you've got about 15, 16 minutes. Take a mental break if you need it, but I recommend maybe trying some of the homework problems. Your homework is that 9.4 worksheet, our last worksheet of the unit.